Well, hello everybody, and welcome to our last lecture. This is Chapter 13, Correlation. For those of you who have been listening to these online lectures, I can't believe we're at our last one. I'm sure you're pretty excited about it. So, Chapter 13 is on correlation. This is kind of a very different type of statistic than we've been doing. A lot of students really enjoy correlation and seem to understand it. I think it's easier than ANOVA, so hopefully you'll enjoy this chapter. We'll talk today about the meaning of correlation and the Pearson correlation coefficient. So first we're going to spend a bit of time talking about what correlations are before we work on the math in terms of how to compute a correlation coefficient. But a correlation is a statistical method that's used to measure and describe relationships between two variables. A relationship exists when changes in one variable are accompanied by consistent and predictable changes in the other variable. Now this is where things get different. For a correlation, you have two variables, and both variables must be on a continuous or numeric scale. So both variables must be numbers. Up until now, we had two variables. Our first independent variable was a category, which broke our sample into groups, either two groups, which would be a t-test, like let's say we were comparing people who took a medication to a group who was on a placebo for their level of anxiety. In that case, our independent variable was categorical. People were either in the group that took the medication or people who were in the placebo group. But now our independent variable and our dependent variable, both variables are numbers. So for example, let me pull this whiteboard up. Maybe we want to look at SAT score. Let me do it this way, SAT score and GPA. In this case, we've got two variables, SAT score and GPA, and both are numbers. So for person one, their SAT score, and I don't even know the range of SAT scores anymore. They keep changing them. Let's say they got a 2,000 on the SAT, and their GPA was 3.6. And person two on the SAT, they got an 1,800, and their GPA is 2.7. And person three, their SAT score is 2,100, and they have a 3.7. Regardless, and again, I don't even know if these are correct SAT scores at this point, but you have two variables, SAT and GPA, and each one is a numeric or continuous variable, and every person has a score on both variables, right? Everybody in our sample will have an SAT score and a GPA. So in order to run a correlation, this is what you need. Two variables that are both on a numeric scale, a number scale. And we'll practice quite a bit of those throughout the day. So we're going to end up computing a correlation coefficient, which is a statistic that will tell us about the relationship between those two variables. We'll talk about that these correlation coefficients can be positive or negative. They fall between -1 and 1, so the smallest correlation coefficient you could get is -1. The largest is +1. It's usually a decimal. And if you have a score that is, if you compute a correlation coefficient that's greater than 1 or less than -1, you know you've made a mistake in your calculations. Okay. Here's an example of a correlation. And we usually start with a scatter plot, which is this type of plot here, but let's take a look at what our data looks like. In this case, we're looking at family income and its relationship to students' average grade on a test. So you can see here are people in our studies. Person A their family income is $31,000. This is in thousands. And the student's average grade is a 72. Person B, their family income on average is a $38,000, and the student's average income is 86. Person C, their family income is $42,000, and their average grade is an 81. So you can see we have two variables. Both variables are scored on a numeric scale, a number scale. Every person has a score on both of these variables. And for a correlation, we start to look at a relationship between the variables. We often start with a scatter plot. So in this case, here's our plot. We have family income in thousands here, student's average grade on the y-axis, and each one of these dots represents a person in the study. So in this case, the person with $31,000 for their family income and an average grade of 72, that's this dot here, right? $31,000 and an average grade of 72. And over here, this person of $174,000 and a 95, $174,000 and an average 95, that's that point there. And once you plot all the data, you can look to see if there's a relationship. And what does this relationship look like to you? Well, hopefully you can start to see that as we're seeing that when people have lower family incomes, they tend to have lower grades. And the people who have higher family incomes tend to have higher grades. So there does look to be a relationship here. And I'm going to explain to you coming up right now how we actually look for that statistically. I'll just go backwards. No, I just have the same slide again. Sorry about that. All right. So correlations. A correlation looks at two aspects of the relationship between two variables. We look at the direction and the strength, and we're going to spend a bit of time right now talking about the direction and the strength and how you interpret that. The correlation coefficient that we're going to calculate is called the Pearson product moment correlation coefficient. Wow, couldn't be a longer name. It's represented by a lowercase r. It's also called the Pearson R or correlation coefficient, but like we've had, we started this class looking at z-scores, right, a z. Then we went to t's. And then for ANOVA, we went and studied the F ratio. For correlation, we're talking about a lowercase r. Okay? And there are two main components of the correlation coefficient. As I said, strength and direction. We're going to interpret the sign as a positive or negative, and that's going to tell us something about the direction of the relationship. And then we're going to look at the size in terms of between 0 and 1. And that'll tell us something about the strength, with a correlation of 0, meaning no relationship at all between these variables. So we're going to start with looking at direction, and this is over here. When we compute a correlation, we're going to end up with something like r equals positive 0.32. or r equals negative 0.67. You're going to end up with something like this. When we're looking at the direction of the relationship, the only thing you're looking at is the sign. You're ignoring the number, and all you're looking at is the sign. Is the number you compute positive for your correlation, or is the number that you compute negative? And that actually tells us a lot about the direction of the relationship. So correlations can be positive, negative, curvilinear, or no relationship, and we'll go through those right now. A positive correlation, so if you end up computing a correlation and the sign is positive, what that tells us is the variables tend to move in the same direction, meaning as one variable goes up, the other variable goes up. When one variable goes down, the other generally goes down. An example of that is here in this completely made up data. But here we're looking at years of education and hourly salary. And what do we see here? We see this line kind of going upwards from left to right. When you have a scatter plot, if you notice a line going upwards from left to right, we're talking about a positive relationship, which is telling us that when people are low on one of the variables, like years of education, they tend to also be low on the other variable, hourly salary. And when people are high on one variable, like years of education, they tend to be high on the other variable of hourly salary. So when you're low on one, you tend to be low on the other. When you're score high on one, you tend to score high on the other. And you can see that, like here's someone who has like 8 years of education, left school in 8th grade, and they make $5 an hour, which at this point isn't even legal, right? That's way below minimum wage, but nonetheless, it's our made-up data. And then over here, when we've got people who are above 20 years of education, right, they've gone on to high school, college, graduate school, they're making $25 an hour, more money. Okay? And so that is a positive relationship. Now, is it true for everybody? Can we say that it's 100% that the more education you have, the higher your salary will be? No, right? When we're talking about correlations, we're talking about general trends. And sometimes students will say, well, but I know someone who didn't graduate high school and they make, $100 an hour. So this can't be a relationship. No, this still is a correlation between the variables. It's on average we see this trend. Not that every single person would follow this trend. And in your mind now, you could try to think of some other variables you would predict could be positively correlated. Try to do that maybe for a second here and think, what kind of variables, as you go higher on one, you would tend to be higher on the other, and people who are lower on one tend to be lower on the other. So you can think about that to yourself. All right, so that's a positive correlation, and you know it's a positive correlation if the R that you calculate is a positive number. Here's another one. Association between variables for positive correlation. Again, as you're low on one, you're lower on the other. Higher on one, you're higher on the other. Here's SAT and GPA. That's the one we just looked at. And we've got, as students are lower on on SAT, they tend to also be lower on GPA, right? We've got a 900 and a 2.4. And then as students get higher SAT scores, they tend to have higher GPAs. This again is a positive correlation. Now, what about a negative correlation? We call it a negative or an inverse correlation, and this would be when you compute your correlation coefficient and the sign is negative, right? So negative 0.67 or negative 0.30 or negative 0.27, whatever it is. This one's a little bit more of a brain teaser. This is when the variables tend to move in opposite directions. So as one variable goes up, the other generally goes down. When one variable goes down, the other generally goes up. If you are below average on one variable, you tend to be above average on the other, and vice versa. So here's an example of a negative relationship. Let's, first of all, you can see this is like a downward sloping line from left to right. If you see something that looks like that, you know you're talking about a negative relationship or a negative correlation. And let's say this x-axis is hours of watching TV, and this y-axis is GPA. So this would be a negative relationship, so that people who are very low on hours of watching TV, right, they don't watch any TV, they have very high GPAs, right? They have 4.0s because what else are they doing if they're not watching TV? They must be studying. And people who are very high on watching TV, they watch 80 hours of television a week, they have very low GPAs. So this is a negative relationship. And again, you could think about some variables that you could think of that might be negatively correlated. And again, remember, it doesn't have to be everybody. We could have someone who, does watch a lot of TV, but look, they tend to have a relatively okay GPA, or we could even have somebody up here that has a pretty good GPA. Not everybody, but a general trend. Here's a negative relationship between amount of homework copied and final exam. And so we're looking at people who don't copy much homework tend to do better on final exams, whereas people who copy lots of homework tend to do worse. So this again would be a negative relationship. And here's another one. Time to complete an exam in minutes and grade on the exam. This is an interesting one. That people who take less time to complete an exam, they're low on time to complete an exam, tend to do better on the exam. And people who take a very long time to complete an exam, they're higher on that variable, tend to score lower on the test. So again, these are all negative correlations. There is a special case of what we call a curvilinear relationship. A curvilinear relationship is when there's an increase in one variable that's associated with both increases and decreases of the other variable. One of our most famous curvilinear relationships is the relationship between anxiety and test performance, and this is actually a true relationship in the psychology literature. And what we find is when people are very, very low on anxiety, they tend also not to do very well on tests. Why would this be? Well, you can imagine these are the people who don't really care, right? There's a test, I'm not worried about it, whatever. I still want to go out with my friends. There's a movie I want to see. And then what happens? They come in to take the test and they don't do very well on it. But we also see that people who have very, very high levels of anxiety don't do well on tests. And these are people who have test anxiety, right? They come in, their mind goes blank, they can't think clearly, they can't answer the questions because they're too nervous. But it turns out that a moderate level of anxiety, those are people who tend to do the best on tests, right? These are people who think, oh my gosh, I have a test coming up, I am a little bit nervous, this week I'm not going to hang out with my friends, I'm going to instead go to the library, and the night before I'm going to get some good sleep, and then they come in and do the best. So curvilinear relationships, this is when an increase in one variable, like an increase in anxiety, tends to lead to both increases and decreases in the other variable. This is important to note, mostly because when you are first gathering your data and starting your analysis, we usually would start with a scatter plot, which would show us, do we have a positive relationship? Do the points fall in a negative relationship? Or do they maybe fall in a curvilinear manner, which could look like this, a upside down U. You could find a relationship that looks like a U-shaped curve, or any other kind of complicated relationship between the variables. The issue is that if you do find a curvilinear relationship, you don't want to run a Pearson correlation coefficient, Pearson R, because our Pearson R is looking for a linear relationship between the variables. It's asking, or the statistic that we're doing will tell us how are the two variables related in a linear way or in a line. And if you find that your data is curvilinear like this, if you run a Pearson R, if you calculate a Pearson R, which is looking for the linear relationship between the variables, guess what you would get if you put this data into a Pearson R equation? It would say 0. It would say R equals 0. R equals 0. There's no linear relationship between those variables. And if you hadn't plotted your data first, then you might say, well, gosh, there's no relationship between anxiety and test performance because R equals 0. Correlation is 0. But that's only telling us the linear relationship, and there is no linear relationship between these variables. In fact, there's a very beautiful curvilinear relationship, and we would do a different statistic for that. In this class, we're only going to be looking at linear relationships, but you still want to be aware that more complicated relationships between variables do exist. Lastly, we might have no relationship between two variables, and that's possible too. In this case, so your scatter plot would look like just a big random array of dots that have no pattern to them. Let's say this independent variable here is shoe size, and our dependent variable here is IQ. Well, there's no relationship between shoe size and IQ, and you can see that here. You could have small feet and a low IQ. You could have small feet and a high IQ. You could have large feet and a low IQ. You could have large feet and a high IQ. There is no relationship at all. Okay? So in terms of direction, as we said, if you've got an upward sloping line, we're talking about a positive correlation. Here's one between temperature and beer sales. The lower the temperature, the less beer is sold. The higher the temperature, the more beer is sold. Positive relationship. And if you plot your data on a scatter plot and you have a negative downward sloping line, then we're talking about a negative relationship. Temperature and coffee sales, right? Lower the temperature, the more coffee is sold. Higher the temperature, the less coffee is sold. Okay. You can do this as an example to see if you can figure these out. These are variables with two variables, and I'm wondering what you think would be the direction of the relationship. Would it be positive, negative, curvilinear, or no relationship? So you could pause this here for just a second and try to work out what you think. There's really no right or wrong, but just try to think about what your answers would be. So pause it here. And hopefully you look through this. We can go through it together. Age and health. What do we think? Younger people are typically healthier than older people, so negative relationship. The younger you are, the better your health. The older people are, the less healthy they are. GPA and hours studied, and hours worked per week. Again, maybe that's a negative correlation. The less hours studied, the higher the GPA. The less hours worked, the higher the GPA. The more hours worked, the lower the GPA. That could be a negative correlation. Air pollution and asthma. Maybe that's a positive correlation, right? The less air pollution, the less cases of asthma. More air pollution, more cases of asthma. GPA and alcohol consumption. Negative correlation, right? The less alcohol people consume, the higher the GPA. The more alcohol, the lower the GPA. Sexual partners and STDs. What do we think about that? The less sexual partners, the less potential STDs. More sexual partners, potentially more STDs. So a positive relationship there. We did SAT scores and GPA. Positive relationship, right? Lower the SAT scores, lower the GPA. Higher the SAT scores, higher the GPA. Although when I talk about this in class, many students say no relationship, and I do understand that as well, that it doesn't matter. Students think what you get on your SAT, you can still do very well in college. Smoking and longevity. Well, the less you smoke, the longer you'll live. This is a negative relationship. The more you smoke, the less long you'll live. And then studying efficiency and caffeine consumption. This one might be curvilinear. I would say it's curvilinear. right? Because what happens if you have 0 caffeine and you're trying to study statistics? You're probably going to fall asleep. But if you have too much caffeine, one of those huge, giant, you know, I don't know how many shots they put in of espresso in those big cups at Starbucks. How do you study then? Not very well also, right? You're very distracted and looking around and wondering what's going on and what are all the noises and, ooh, I wonder what my friend is doing, right? But there's kind of a perfect level of caffeine, right? 1 cup of coffee or something like that, that helps you focus, helps you study, and that might be the optimal caffeine consumption for studying. Again, no right or wrong. You might have had some different answers, and if you could at least explain your answers, that's the important thing here. Now remember, we found all of this information out just by looking at the sign of a correlation coefficient. Was it positive or negative? And it's told us a lot. What about actually looking at the number? So this would tell us about the strength of the correlation. And so back to here, R equals positive 0.32 or R equals negative 0.27. So now let's just look at the number. Doesn't matter if it's positive or negative, like we're just looking at almost the absolute value of the number, of the correlation. And that tells us about how strongly those variables are related to each other. So as I said, if you have a correlation coefficient of 0, well, there's no relationship between those variables. If you have a correlation of 1, positive 1 or negative 1, that is a perfect correlation. And that would look like every single point falls exactly on a particular line, like this. Every single dot falls perfectly on a line. Now, how often does that happen in psychology? Pretty much never, right? Human behavior is much messier and much more difficult to predict. We don't usually get things like this. But this could be something like height of something in inches, and then height of something in feet, right? If something is 12 inches, it's always 1 foot. If something is 24 inches, it's always 2 feet. If something is 36 inches, it's always 3 feet. There would never be any point that falls off of these lines because it's always the case. Every time you measure something that's 12 inches, it's always 1 foot. This is a perfect relationship, and you would never have any dots that don't fall directly on this line. So this is a perfect positive correlation. Something we almost never see in psychology. Well, we do never see in psychology. You could also have a perfect negative correlation. The closer your correlation is to 0, the weaker the relationship between the variables are. The stronger the relationship, the closer your decimal is to 1. And this is from your book in terms of how strong is an association. We'll call a small correlation about 0.10, medium about 0.3, and large about 0.5. Okay? Perfect positive correlation. Here. Number of absences and exam grades. Do you think this really would be a perfect positive correlation? No way, right? Everybody, all the time, if you miss 2 classes, you will always get a 40 on the exam. No. This is nothing you would ever see in psychology. How about a perfect negative correlation? Again, number of absences and exam grade. If you have 0 absences, does that mean you'll always get 100% on an exam? No way, right? You could have 0 absences and still fail the class. This is what you would never see in psychology. we get things that are a lot more messy, and I'm just going to go to this second slide here, just to go through it with you. So these dots that all fall on this perfect upward sloping line, that's a perfect positive correlation. And these dots that are falling on this downward sloping line, that's a perfect negative correlation, both of which we will never see in psychology. Here where we've got a totally random array of dots, that's a correlation of 0. There's no relationship between these variables. Down here in part D, this is a correlation of positive 0.80. So it's a positive correlation. We've got generally this upward sloping line. And the dots don't fall exactly on a line, right, like they did up here, but they are still really clustered very tightly together. This is a strong relationship. Again, something we would never see in psychology when you're studying people. Now this looks a little more like psychology, a correlation of 0.30. Again, you've got generally an upward sloping pattern, so we know it's a positive relationship. But these points are very widely spread. This would be kind of weak or moderate type of relationship. And then here's a correlation of negative 0.20. Now we've got generally a downward sloping line. And again, there's even more variability in the pattern of the dots. And so this is an even less strong correlation than the 0.30. Okay, so check your learning, which is stronger, a correlation of 0.25 or negative 0.74? What do you think? Hopefully you said negative 0.74. Remember, when we're talking about correlations, doesn't matter positive or negative, we're just looking at the number itself, the decimal itself. And the closer that decimal is to 1, the stronger it is. So this 0.74 is a much stronger correlation than 0.25. All right. One thing about correlations, hopefully that strength and direction is making sense to you. One thing about correlations, and statistics teachers like to say, correlation does not mean causation. And this is really important. When we're talking about correlations, we're talking about associations between variables, patterns between variables. But we haven't done a research study. All we've done is asked people some questions and looked at what was naturally occurring in the real world. So, sorry, let me just come over here. In this case, we just measured how long it took for people to take an exam and what their grade was. We didn't do an actual experiment where we manipulated something, where we put people into different groups. And you'll talk a lot more about that if you take a research methods class in terms of the difference between correlational research and, excuse me, experimental research. But what you need to know is that correlation doesn't mean causation, which is to say that let's say you found a correlation coefficient of 0.91. That's a very strong positive correlation between eating ice cream and number of people who drown. So the more ice cream that's eaten, the more people who drown. So does that mean that eating ice cream causes drowning? If you find a correlation between amount of ice cream eaten and drowning deaths, can we say that eating ice cream causes people to drown? Well, that doesn't make a lot of sense, right? There are sometimes other variables, we call them third variables, that might account for this relationship. What would be a third variable that might account for people eating more ice cream and people drowning more? Hopefully you've come up with the idea of temperature, right? The hotter it is, the more ice cream people tend to eat, and the more people swim, right? They're around the water, they're in swimming pools and beaches and lakes, and so the more people drown. So even though we find an association between two variables, we can't say that one variable causes the other to occur. We just have to use words like those two variables are associated, or there's a relationship between the variables, or there's a correlation between the variables, but you may not use the word cause, because the only time you can use the word cause is when you have done an experiment, and then we can talk about cause and effect. So correlation does not indicate causation. For any correlation that you get, there are three possible explanations for it. Let's say we're looking at the correlation between drinking alcohol and GPA. And let's say we find, let me write this down. Let's say we find correlation that the more alcohol someone drinks, the lower their GPA. So this is a negative correlation. Okay, more alcohol, lower GPA. So there are three possible explanations here. One is that it is possible that drinking alcohol causes GPA to go down, right? That's probably why I did this study. Maybe I'm thinking drinking alcohol is a problem for students and their grades, and so I find this relationship. And so that is one possibility, that drinking alcohol causes people's GPA to go down. There's also the possibility of what we call reverse causation, that it could be that having a low GPA causes people to drink, right? They're like, oh my gosh, I'm failing out of school. I'm so upset. My parents are going to be angry, and I'm going to start drinking to deal with this problem. So it could be the original direction of the relationship, that alcohol causes GPA to go down. It could be this is what we call reverse causation. It could be that having a low GPA actually causes people to drink. Or there could be a third variable. What's a variable that might cause people to drink more alcohol and cause people's GPA to go down? I don't know, maybe something like stress. So people who are more stressed tend to drink more alcohol. People who are more stressed tend to have lower GPAs. And so there isn't actually a causal relationship between these two variables. But there's some third variable that we didn't study that's actually responsible for the relationship that we found, right? Stress, depression, could be another one. Okay, so the limits of correlation here is correlation does not indicate causation. We could have variable A affecting variable B, causing variable B. We could have the reverse causation, or we could have a third variable that's affecting the other two. So you need to be aware when you get a correlation not to jump to the conclusion that, oh, that one variable is causing a change in the other. With correlations, there's multiple explanations. Okay, so the Pearson correlation coefficient, this is a statistic that tells us about the linear relationship between two scale or numeric variables. So P is linear relationship between two scale variables. It's italicized by, it's symbolized by the lowercase letter r for sample data, and it's symbolized by the Greek letter rho, which kind of looks like a P, when we're talking about population. The correlation coefficient can be a descriptive statistic. As we've been talking about it, it's a descriptive statistic telling us about the direction and strength of an association between two variables. But it can also be used as an inferential statistic where we do a hypothesis test to tell us, based on our sample data, if we see a correlation in our sample, would we also see that correlation in the population? And is the correlation coefficient in the population likely to be different from 0, meaning there's no correlation? So we're going to go through the steps of a hypothesis test, which we've done many times at this point, but now we're going to do the hypothesis test for a correlation. Okay, so to compute a correlation, you need two scores for every individual, a score on variable x and a score on variable y. Remember, those scores have to be on a numeric scale. And if you have other scales of measurement, there are other correlational methods that you can use. There are a number of different types of correlation. We're only talking about one. We're talking about that Pearson product moment correlation in this class. But you should know that at least there are other correlations that you might end up using if you move on and do more statistics in your future. All right, the formula that we're going to use is right here. The Pearson R is equal to the sum of products over the square root of sum of squares x times sum of squares y. Your book has this formula, which is exactly the same thing. Instead of using sum of products, this is the sum of the products here, which I'm going to show you how you do. Over the square root of sum of squares x over sum of square y. I think this formula is a little bit easier to deal with, and we're going to fill out a chart that I think, again, makes this whole computation pretty simple. If you like the one in the book, you're welcome to use that. Either one is fine. So let's take a look at how to compute a correlation coefficient. Here are our scores. We're looking at the relationship between cups of coffee, that's our x variable, and restlessness rating, that's our y variable. And we always set this up, x and y, with x being kind of what you think is going to be causing a change in the y variable. So sort of as an independent variable as x and a dependent variable as y, even though you're not really manipulating your independent variable. So in this case, we're thinking the amount of cups of coffee somebody drinks is going to affect their restlessness. And here are people, the individual people in our sample. So this person had 1 cup of coffee and they had a restlessness rating of 2. Let's say they sit in your laboratory and there's a research assistant who's rating how restless they are. This person had 2 cups of coffee and their restlessness rating was 3. 2 cups of coffee, their restlessness rating was 4, etc. All right, so take out your calculator so you can see how to get these calculations. But we've done this many times before, and this table is kind of similar to what we've done before. First thing we need to do is get the mean for x and the mean for y. So you're going to add up all the scores and divide by the number of scores. 1, 2, 3, 4, 5, 6, right? Add up the scores, divide by the number of scores. Now we have to do our deviations just like we've done before, but we have to do x and y. So this is going to be the score minus the mean, gives you the deviation. And then again, so this is our x deviation, and then you need to square them. So you might, when it's already in your calculator, then just square it to get your squared deviation here. 2 minus your mean for x will be your deviation, and then square it over here for your x deviations. And then you're going to do the same thing here for restlessness rating. You're going to get your mean, and then you're going to do your score minus your mean, that's your y deviation. This score 3 minus the mean, that's this deviation here. And then again, each time you'll square it, because if you remember what happens when you add up your deviation scores, you end up with 0 every time. Once you've got your square deviation scores, you sum them up. So you get sums of squares x and you get sums of squares y, just like we've done before. And the only different part is this last column here, sum of products, SP, sum of products. The products are multiplication, and you're multiplying your deviation scores together, right? This x minus the mean of x, that's this column here, times y minus the mean of y, that's this column here. So this times this gives you the product. This one times this one gives you the product, okay? And then add them up, that'll be sum of products. So maybe try to do that for a second. Pause this here. And if you've done it, you should get data that looks like this. So our mean for cups of coffee was 3. The mean restlessness rating was 4. 1 minus 3 is -2. That's your first x deviation. And then square it gives you 4. 2 minus 3 is -1. Square it gives you 1. There it is again. 4 minus 3. 4 minus 3 is 1. Square it is 1, etc. And then you also do the same with the restlessness rating, right? 2 minus the mean of 4 is -2. That's our y deviation. And then you square it. That's 4. 3 minus 4 is -1. Square it is 1. And you go all the way down there. Then you've got your sums of squares. So sums of squares for x is 12. Sums of squares for y is 10. And then the different one here is sum of products. And remember, you're multiplying the deviation scores together. This is really important to remember your signs because this is going to be where you get a positive or negative correlation. So -2 times -2, remember, negative times a negative is a positive, so it gives you +4. -1 times a -1 is a +1. -1 times 0, that's 0. 1 times 1 is 1. 1 times 0 is 0. 2 times 2 is 4. Okay? Then you add those up and you have sum of products there. And that's everything you need to calculate your correlation coefficient. There's our formula. Sum of products over the square root of sum of the squares x times sum of the squares y. So our sum of products was 10 over the square root of 12 times 10, right? Sum of the squares x was 12, sum of the squares y was 10. So it's 10 over the square root of 120, which is 10 over 10.5, which gives you a correlation of 0.91. All right, so this is the correlation that we see in our sample. In our sample of 6 people, we found a very strong positive correlation, right? The more cups of coffee someone drinks, the more restless they are. The less cups of coffee, the less restless. And it's a very strong, right? 0.91. Maybe it looks like somebody made up the data, like you're a teacher. Yeah, because we would never see something as strong as this in real research. But anyhow, there it is. So now the question is, would we see this correlation in the population? Or is this just a sampling error? So we go through our hypotheses. So the null hypothesis is that rho, remember that's the correlation in the population, rho is equal to 0. That's the null, that there is no correlation. Just like our null hypothesis has always been, the independent variable has no effect. So our null hypothesis here is that in the population, there would be no correlation. The correlation would be 0. And our alternative hypothesis is that rho is not equal to 0, that in the population there is some correlation. And it might be positive or it might be negative, but it won't be 0. Step 2, degrees of freedom and a critical value. Degrees of freedom for a correlation is n minus 2, where n is your number of pairs. So in this case, we had 6 pairs minus 2 is 4. There is an R table in your book. I also posted one online. So here we go. This is the one that's online. Degrees of freedom is 4. We're always doing a two-tailed test, and I said 0.05 significance value. And as you do that, you see the critical value is 0.811 right here. So we're always, for this class, looking at a two-tailed test. We'll never look at the one-tailed test, always two-tailed. And I'll tell you, is it 0.05 or 0.01, in this case 0.05 level? Degrees of freedom 4 gives you 0.811 as your critical value. Okay, this is from another book, but same thing. 4 degrees of freedom, 0.05, there's our critical value. Find your R, step 3, which we already did. R is 0.91. So we've got, there we go, some kind of critical R at 0.811, and it's positive or negative. And we found that our R, our correlation, was over here, right? It was 0.91. So it's more extreme, or it's in the tails, which means that we will, as before, reject the null. Our obtained R of 0.91 is greater than the absolute value of the critical R of 0.811. And now we're going to substantiatively make a conclusion, and this is a 0.91, it's positive. So we're going to say, as cups of coffee increases, restlessness rating increases. That's our conclusion based on this correlation. It's a positive correlation. If it was a negative correlation, we'd say, as cups of coffee increase, restlessness rating decreases. All right, let's try one more. We're going to look at fruit servings per day as our X variables and days absent from school as your Y. So we're wondering, is there a relationship between how much fruit students eat and how many days they're absent? So again, these are two variables. They're both numeric variables. Each person in the study has a score on both. So this person eats only 1 serving of fruit a day, and they're absent 6 days. They've been absent 6 days in the semester. 4 fruit servings, 4 days absent. All right, so what I want you to do is try to fill this chart out with getting the mean of X, the mean of Y, the X and Y deviations, the square deviations for X and Y, then you add them up for sums of squares, and then sums of products, remember, are the multiplicate when you multiply your deviation scores. This one times this one, okay? And then add them up for sum of products. So go ahead and pause here. Be sure you can do this. Oh, look, I have a graph for you. Here's our scatter plot. What does it look like we're looking at? A positive or negative correlation. Hopefully you can see it looks like a negative correlation between fruit servings and days absent. The less fruit people eat, the more absent they were. The more fruit people eat, the less they were absent. All right, here's the computations. So fruit servings a day, the average was 7. Realizing this probably should say per week because I don't know how many people eat 13 fruits a day. Anyhow, the average was 7. Days absent, the average was 3. Your deviations, right, 1 minus 7 is -6. Squaring -6 gives you 36. 4 minus 7 is -3. Squaring -3 gives you 9. And you would finish that for the X deviations and the X squared deviations. Now what about days absent? So 6 minus the mean of 3 is 3. Square it is 9. 4 minus the mean of 3 is 1. Square it is 1. 2 minus the mean of 3 is -1. Square it is 1, etc. And then you'll get your sums of squares y. Now your sum of products here, or your products, or you're multiplying the deviations. -6 times 3 is -18, right? -3 times 1 is -3. 0 times -1 is 0. 3 times -1 is -3. 6 times -2 is -12. And when you add up the negatives, you get your sum of products of negative 36. So we go to our hypothesis. Our null hypothesis is that rho is equal to 0, that in the population there's no correlation between these variables. The alternative or research hypothesis is rho is not equal to 0, that in the population there is a relationship between the variables, maybe positive, maybe negative, but it won't be 0. Critical value and degrees of freedom. So degrees of freedom is n minus 2, the number of pairs. We had 5 pairs minus 2, which is degrees of freedom of 3. Two-tailed alpha 0.05. So we'll go to the critical table, critical R table, of 3 degrees of freedom, 0.05 significance is 0.878. And you can see these are huge critical values. You would never do a study where you're looking at a correlation of 5 people, right? That's why these are so high. Okay, so 0.878. And let me get this. So we've got 0.878 over here, negative 0.878 over here. And we need our correlation coefficient to be beyond that. So now we do our correlation, sum of products over the square root of sum of the squares x times sum of the squares y. So we've got negative 36, that's our sum of products, over the square root of 90 times 16. So negative 36 over the square root of 1,440. Negative 36 over 37.95, which gives us a correlation of negative 0.95. Huge correlation. So negative 0.95, that's over here. Again, it's in the critical regions, it's in the tail. And so in this case, we would reject the null. Our obtained R of negative 0.95 is greater than the absolute value of our critical R, plus or minus 0.878. Substantiatively, as number of servings of fruit per day increase, the number of school absences decrease, right? That's our negative correlation. And I think we have finished correlations and finished the last lecture and chapter that we have to do in statistics. So you should feel good and proud of yourselves to have gotten through this. And good luck, and then we'll talk about the end of the class coming up. Thank you. Bye.